attendees can now hear you.
Good morning, and welcome to our webinar on protein shifting. My name is Suha Osoilu, and I'm the Director of Operations at HMPS. I would like to start with a quick introduction to the Hosokawa Group before we get going with our presentation. The Hosokawa Group, one of the largest powder processing companies, is formed of numerous divisions around the globe with an annual revenue over $500 million. Our primary business is providing solutions to our customers' size reduction, classification, mixing, drying, and containment requirements. We accomplish this with 1,500 employees, 5 test centers, and a presence in all 5 continents. Hosokawa Micron Powder Systems, located in Summit, New Jersey, with its full sales, engineering, service group, and test center, is the unit responsible for the servicing of the North American market. Our presenter today, Alex Lenge, is a food specialist from our sister company, Alpine, located in Augsburg, Germany. Alpine, an innovator in a powder processing field, also has a blown film division. With that, I would like to turn the microphone to Alex for our presentation.
Thank you, Suha. Good afternoon, ladies and gentlemen. My name is Alexander Lange. I have started my career with an apprenticeship as a mechanical engineer and continue and expanded my education with an engineering degree at a German milling school. Since 8 years I'm working for Hosokawa Alpine, and due to my experience and my favor for a good food and tasty food, I'm established as a specialist for food application in the pharma food division. Since several decades, Hosokawa provides the protein shifting process to establish a protein concentrate in a dry matter-based process. The following presentation will be going to different topics. We are starting with the process and machines. The foundation of the protein shifting process can be described with, The foundation of the protein shifting process can be described with a disagglomeration of an endosperm, abscission of protein particles from the starch particles in the air classifier. Alternatively to the starch, fiber particles are to separate.
Alex, I think we're losing communication. We apologize, but I think there's a small problem with the communication here. If you can give us a few minutes, we'll sort this up and continue from the location. So bear with us for a few minutes. Is he connected? Alex?
So are we online or not?
Yes, we are, Alex. Please continue. We got cut off. Please continue from the process and product possibilities slide.
Okay. As we can see, the process and product possibilities are divided into the starchy seeds and oily seeds. Starchy seeds, like wheat, peas, or beans, are using, after a fine grinding and air classification, into a protein concentrate and, of course, a starch concentrate. Oily seed as an alternative, for example, extracted soy or blue lupines, are even grind, sifted, and air classified, and then separated after the air classification into a protein concentrate and a fiber concentrate. next. We are using for the fine grinding step different possibilities for mills. One of the possibility is a wide chamber twin drive mill, which takes the material as wheat or beans, for example, into the grinding zone. Via the pin mills, the material is disagglomerated and destroyed, and remaining on the product outlet side to the next process step. Alternatively, and with a higher fineness range achievable, the air classifier mill takes the raw material like wheat or beans, for example, in the grinding chamber. The material is distributed via a rotating disc to the grinding track, which is static, and the airflow, which enters here under the number 5, into the milling chamber, lifted up the material to the air classifier wheel. This classifier wheel, rotating on a very high spin, is ducting the material through the lamella, and only the fine particles can escape out of the process, out of the milling process, with the air. The coarse particles are remaining into the grinding chamber and regrinded until they have the finest request. After the grinding step, the air classification is a very important step. Especially here, the distribution of the raw material or the ground material. The material is falling in a free-falling way against an airstream and disperse here in this dispersing area. Fine particles are lifted up with the air and transfer even to a classifier wheel. The coarse particles falling down and is discharged with a rotary gate on the bottom side. If the particles are not in the exact particle range and coming through with the air through the classifier wheel, the materials are removed out of the classifier and falling down to the core side, on the bottom side. This allowed us the possibilities of separation the protein particles from the starch or from the fiber content. A typical installation of a dry matter-based protein shifting process looks like as we see it here. We feed the material into the mill with approximately 10% on wheat flour protein level, disagglomerate this endosperm, and feed the material, the ground material, into the air classifier. The air classifier are separated now the material into the fines, with approximately 20% of yield and 20% of protein on the wheat base, and into the coarse, which is approximately 80% fraction and 75% protein. We are using in the standard process the pin mill, double rotating, the air classifier turbo blacks to separate the particles, the protein particles from the starch particles, and create a low protein fraction on the coarse side and a high protein fraction on the fine side. Depending on the raw material and on the request of final material, alternatively installation is by using the air classifier mill. The principle of the process is similar. We are fed the raw material into the grinding mill, air classifier mill. The ground material is lifted up with the air to the air classifier. And here we are create again the protein concentrate with a high protein fraction and the low protein fraction on the coarse side. Process parameters will be the next. As we can see the difference, or at the beginning of my presentation, I'm explaining that the basic of the protein shifting process is a disagglomerate of the raw material. Depending on choosing the mill type, we have different possibilities to disagglomerate the particles. We can see the pinmill is a much coarser particle distribution compared to an air classifier mill. This explains the better results of the final material. If you take a look into the air classifying process, we have here an example of wheat flour and a typical particle distribution. Roughly in the top size, 117 microns. As an SEM picture, you see here the conglomerate of starch particles which stick together in the endosperm body. This material is ground on an air classifier mill, and we see here a concentrate at 20 microns, which is at the wheat material, the primary starch particle. Very important, we see it in the SEM picture, the disagglomeration of the endosperm body. There is no any more complex structure available. Loosened proteins and loosened starch particles. This material, I'm explained before, some slides before, we are fed into the air classification, and we are concentrate in the air classifiers the particles which are below 20 microns. These particles are typical the protein particles. Of course, we are working in the dry matter base and we are not 100% exactly. There is still some coarse particles which drops through the air classifier wheel and enters into the fine fraction. But the concentrate is here below 20 microns, and we see we have a very fine flakes available. On the opposite side, there is the starch fraction, and we see here a concentration above 20 microns. Even in the SEM pictures, we see more or less very pure starch particles available. In the dry matter base, I already announced this one. Some leakage will be available. That is the reason protein particles of 2.5 microns are very sticky, and the additive forces are very, very strong, which results that some protein particles are sticking on the starch particles and transfer into the starch fraction. Anyway, on the wheat flour, the typical process scheme looks like that we are fed 100% with approximately 12% protein. We are crushing in the air classifier mill, still have 100% and 12% protein, and separated right now approximately 25% into the finer steels with roughly 24% of protein. And alternatively, you have 75% starch fraction with a protein content of, let's say, 8%. Low protein flour up to 6% are available. Alternatively, as an example, the green peas, we are starting not with 12%, we are starting with 25% protein, still have 100% material. Using the air classifier mill, disagglomerate the kernel, still have 25% protein, but comes up now on a protein level of 55% and a yield of 35%. This is a typical alternative to fish meal, for example, protein concentrate for fish. On the starchy side, we have remaining 65% fraction with a protein level of 15% and a starch level of roughly 70%. Starch levels increased up to 75% available. Process results. And here, finally, we can come to the product figures of various raw material. As a flexible installation, typically you can use for protein shifting peas, fava beans, lupins, extracted soy, or even wheat flour, as we have already shown. In the standard process, which is typically a pinmill in combination with the air classifier, we achieve a yield, the finest yield, up to 30% with a protein level of more than 50%. At fava beans, 25% yield of 65% protein level. And for lupins, and extracted soy, we are coming up more than 60% on a very efficient extraction. Wheat flour remaining approximately 20 to 25%, and the protein level of 18 up to 24% available. On the precision process, which is using the air classifier mill and do with the better endosperm disagglomeration, better separation in the air classifier is available, we can increase the yield of protein fraction of more than 5% on still higher protein levels. This is the benefit of the higher precision process. We increase the protein level and still have a very high yield of the material. The next chart is shown the varieties depending on your market and your market request. The installation allowed you to set the parameters, the process parameters, in according to your requirements. A tailor-made material, more or less, is possible with this one. On the bottom side, we have the protein level, and on the vertical side, we have the yield of this one. We see here the finest yield for the soft wheat are in the range of 25 to 15%, and the yield of approximately 20%. We can increase dramatically the yield and even the protein levels when we are using material which is still from the raw material base on a higher level. Peas and beans are typical materials for this one. Market application for the bakery application. The process provides a high protein and low protein flour, and for both of these materials, you have to have a market. Especially for the high protein, a common market is improving for bread improvers or even for frozen doughs, an ingredient for frozen doughs to absorb more water. Even a bread improver for yeast material is application for the bakery application. The starch fraction as a higher amount is using typically for sponge cakes or cakes in any way, wafers, cookies, and biscuits. Especially in the Western world, the household mixes is not needed to have a high protein content. A lower protein is sufficient to make cakes. So this is a typical application, household mixers. Beside of this one, of the bakery applications, there are industrial applications for the low protein flour. At 8%, it is interesting to using as a glue in the cotton cob industry, or to using as a raw material for the starchy industry. As an example, or as a result for German rolls, the high protein provides an additional volume and improves the crumb. For the low protein material, which we are using at wafers, for example, we got a better viscosity with a lower energy and a lower saving raw material cost. For pound or sponge cake, we get better volumes and better mouthfeel. Even the crumb is more stable, which if we're using the low protein material. Coming back to the wafers, you see here a typical viscosity curve for wafer butters. And when you're using the normal wheat flour, you see the pink line, which is always very inhomogeneous. This is the viscosity curve of the proteins and the denaturation afterwards. You need to have minimum 120 grams water per 100 gram flour to get such viscosity curve as the pink line. Very stable and with a lower water content is the blue line. No or less viscosity peaks in this curve, and you get in a faster way this viscosity curve compared to the normal wheat flour. This saving of water for these batters is, of course, at the end saving time in the production and, of course, even saving money. To evaporate at the wafers 20 kilograms of water, you roughly need to have 12.5 kilowatt hours energy. In Germany, for example, we have approximately 8 cents costs, 8 euro cents cost per 1 kilowatt hours. Per 100 kilogram of low protein flour, you save 1 euro when you're using this material for wafer butter. Sometimes, or some industries, are mixed up the material. And here we have the alternative. When we are using the low protein flour, you have cost of approximately 25 euros when per 100 kilogram. If you're using a normal standard wheat flour and mix it up with wheat starch, you have an increasing of 2 euros per 100 kilogram of wheat flour. This is even an example to save money if you're using the low protein material. And this spreadsheet we get from a client. He makes some baking tests, here especially the pound cake, and make an evaluation of different parameters. We can see compared to the wheat flour and wheat starch blending, the volume yield is increased if you are using the low protein flour. Even if you are using a higher protein content as basis, the increase of volume yield is available. Besides of this one, the humidity, which is very important at the pound cake, the mouthpiece and the humidity is much better compared to a standard wheat flour and starch blending. Especially for the situation of food and feed applications, which are typically used the peas and beans as bases, the high protein meal is used as breeding feed, for example, or even in the cosmetic industry. Food applications are a very interesting area too. Low protein meal on the starching side is using typically for alcohol fabrication, or very interesting for food and starchy noodles, in starchy or pudding application. In the feed industry, starch as an energy carrier is typically used as a direct feeding possibility. Sua already announced this one. We have in our company even a blowing film processing division. Sometimes we have even tested the film processing, and the biodegradable materials are coming up very, very strongly. So film processing is even one possibility for using the low protein meal comes from starch. Anyway, the biggest request comes from the food side, and here I found a forecast from the USDA for the next more or less 12 years from this one, and we can see that fish and fruit are increased very strongly in the consumption. This not only due to the demographics, even the food behavior or the consumer behavior are changing dramatically. The protein fraction as an alternative for the fish feed industry to subsidize the fish meal, which is even low in the resources, is one very important alternative. The fish industry are limited in the using the soy material due to the fiber content. Very interesting for them are starchy protein concentrates, which can absorb directly even from a fish. Fish meal with a protein content of, let's say, 60% and more can be subsidized by protein concentrates comes from beans or beans easily. And this, ladies and gentlemen, is the last slide, and I thank you for your attention and open for the question. Sua, you can...
Yeah. Ladies and gentlemen, right now, if you have any questions, you can type those questions in, which I will read out loud if there are any, and then we'll have Alex answer those questions for you. Alex, I got one question so far, and that is asking about the largest capacity systems that was supplied. Could you give an idea about what the largest capacity line that we can supply as Hosokawa?
Yeah, typical. Depending on the raw material for wheat flour, for example, the limitation is here at approximately 3 tons for a single line, and for peas or beans, for example, in the single line, it's approximately 5 tons.
In terms of, there's another question. In terms of the fish meal market, do you see any applications where Faba beans are being utilized?
Well, we already know that Faba beans is one possibility. We did a couple of tests even, but the question is here the resources of raw material. And very often the clients are moved over to the peas because they are more available on the world market. But anyway, beans, Faba beans especially, can be used in the protein shifting process too.
Okay. I have a question here. It says, how do you obtain higher yield with a higher concentration of protein?
Actually, we have to limit it here, or we are talking about concentrates. They are restricted on a range of, let's say, 50 to 60%. If you are looking for more than 70 up to 90%, you have to go to an isolate, which is typically a wet process. And here is depending on the market, the energy requests for this process are more or less not only double higher than our process or than the dry matter process. This is depending on the market. We are limited in the protein level of roughly 50 to 60%. If we're going higher, for example, at peas, more than 60% protein, the yield drops down to less than 10%, which makes not economical this process.
Here's another question. Are lab scale models of the Turboplex air classifier available? And I guess I'll just add to that, are there any shortcomings on the smaller scale?
I didn't got the question right now. Did I understand right that there is a lab scale model, or they are looking for a lab scale model?
The question is, are there lab scale models for the Turboplex? And are there any downsides to going too small on the scale? Yeah,
there is, of course, in the lab scale unit an issue, because the dimensions of the lab scale unit are very, very close, and as I told in the beginning, the particle size are very, very small, so they're getting sticky. As smaller the machines, for example, a small lab scale unit with a diameter of just 50 millimeters, the housing are very close to each other, and this provides then a build-up into the classifier. There is definitely a limitation. We are recommended to use a technical center at Hosokawa divisions for in a range of a minimum 200 kilograms per hour capacity range.
Alex, maybe just to add a little bit, I'll mention that the Turboplex line starts with the smallest 20 millimeter unit, which is currently the Pico line. Yeah. There's a 50 millimeter unit, there's a 70 millimeter unit, 100 millimeter unit, and it goes up from there. in general, what would you say like the smallest unit that you would recommend for typical small-scale trials for customer use? You know, when we're talking about the sticky factor.
Yeah, bigger than 100 dice.
Thank you. Here's another question, Alex. What is the kilowatt-hour consumption of a three-ton wheat flour line? 3 ton an hour, I'm sorry.
Well, let us coming back to the specific energy. And for the wheat flour, we have in the standard process roughly 60 to 70 kilowatt hours per ton. That means 210 maximum for the 3 tons. And in the precision process, to achieve the highest protein content of 24%, for example, we need there minimum 120, up to 150, depending on the wheat. Canadian red hot winter is a very hard wheat, which makes it difficult to ground. A French wheat are more softer. So depending on the raw material, between 120 and 150 kilowatt hours per ton.
Here's a little different question. I guess on the ethanol side, do you have any experience with any applications where, you know, the starch fraction of any legumes being used for ethanol production? And if so, you know, can you give us a little bit of info?
Yeah, we did some tests in a distillery here in Europe, and we found out that the material, the starch material, can be used in the ethanol process. We get a little bit higher yield out of the starchy material due to the better fermentation, because the material are much finer and the enzymatic activities are easier. This results a little bit better yield of ethanol compared to a kernel, for example, or a crushed kernel. The negative sense is that especially at the fibers which are included in this, still included in this starchy material, they are getting to increase the viscosity and create some foaming. Anti-foaming agents are here needed and essential, definitely essential. But anyway, the distillery or the possibility to get alcohol out of the starchy material are a good idea, more or less.
Okay. Alex, I have no other question at this point. So what I would like to tell our audience is, you know what, if you have questions, please, you know, send it in. We'll go to our next slide here, which you could see our contact information. You can email your questions in to me directly, and at which point, you know, I can get you answers offline. And what we're going to do is we're going to go to about a 10-minute break till we start our next presentation, which is on starch activation, attrition milling starch activation at 10:45. And even if you have some questions in the meantime, please forward on, and you know, before we start the second presentation, we can provide answers to those. So bear with us for 10 minutes, and 10:45 we'll be back again. Thank you. Now we can't talk. Welcome back. This is the second part of our presentation this morning on starch activation. Again, my name is Hosokawa, and I am the Director of Operations at Hosokawa Micron Powder Systems. Again, just to give you a brief intro, even shorter than the last time, Hosokawa Micron Powder Systems, located in Summit, New Jersey, is a division of the Global Hosokawa Corporation and servicing the North American market. Our presenter, Alex Lenge, is a food specialist from our sister company, Alpine, located in Augsburg, Germany. And With that, I'm going to turn it over to Alex for this second part of the presentation. One additional thing, if you have any questions, what we're going to do is we're going to have a question and answer session at the end of the presentation, but please feel free to send it in, and at the end, I'll read out the questions for Alex to answer them. Thank you. Alex, please.
Thank you, Sua. Good afternoon, ladies and gentlemen, again. The following presentation is related to our daily eating habits and supports an improvement of baking potential through higher water absorption with the process of attrition grinding. Again, we will have some typical topics, and the first of it is the process conditions. The advantages of water absorption, water as one ingredient in the dough, which takes an important responsibility of dry dough surface, a better machinability of the dough to the drier surfaces, avoiding of water binding additives like gua or pre-channelized flour. It is improving the fermentation and gives water as a carrier of flavors, gives a better taste finally. A softer crumb and the delayed staling are even very important parameters. Water is even a responsibility for a longer shelf life, and last but not least, but very important, it increases the bread yield. If you would like to take an influence on water binding possibilities, we have to realize which possibilities beside of breeding and agriculture are in accordance with water absorption. This chart shows the ingredients of protein, damaged starch or activated starch, and soluble pentosans. Protein, for example, absorbs the same part of water as it available in the wheat flour. Damaged starch, which comes always from a mechanical treatment, roughly in a normal flour mill, 5% of damaged starch, takes 3 times higher water absorption. Compared to the content of pentosans in the wheat flour, the absorption of water for these fibers are very high, up to 10 times higher is the water binding possibility. Of course, in white flours, as we typically use it, pentosans are not so available. More in the darker flours will be available. Anyway, in the sum, the blue columns show then a water binding of roughly 50 to 60%. As we already saw, the content of activated starch or damaged starch are already existing in the wheat flour. The proportion of content of this activated starch is, of course, limited. Compared to the baking volume, you will see the best baking volume is achieved when we are using a very bad wheat flour with 22% of gluten. Activated starch, let's say here is 5%, will be then have the maximum of baking volume. Getting a better quality of wheat, we can increase the bread volume just by adding a little bit more damaged starch to get a better volume of our baking results. In a dry matter process, attrition grinding increased the content of activated starch significantly. The attrition grinding creates the structures on the surfaces from the starch particles and allows the doughing water to enter direct into the starch particles. We see here the starch particles with approximately 25 micron size. The process behind of of these attrition grinding is consists of different machines. First of all, we have a material infeed which is under number 3. The wheat flour enters via a dosing feeder, a loss and weight feeder in this matter, parallel to the stream of steel beads, whose materials are enter into the milling chamber, which is shown here in this slide under number 2. Continuously, the mixture of steel beads and wheat flour are discharged via a through feeder out of the system and are separated in the air classifier under number 4 into pure wheat flour, attrition grind wheat flour, and steel beads, which are recovered by an elevator back into the loss and weight feeder. This picture shown a machine size of ATR 400, which shown here the milling chamber and the outlet opening here, and the gear and driven part at the top section. The material is fed vertically through this mill, and the agitator inside of the mill is agitated the mixture of beads, steel beads, and wheat flour. These processes can be adapted into a milling diagram in different ways. One possibility is to use it just as in a bypass. A passage flour, for example, can be used, or even a stream after the flour mill can be used parallel through the main process or main flour stream. Here, an increasement of, let's say, 2 or 3% is available just by using a 10% ratio through this attrition flour system. Alternatively, the process can be run separately, independent from the flour diagram or milling diagram, for example, in a blending housing. The flour stream will be get in a maximum attrition grinding process to increase the water absorption on the maximum, and the blending will be make available different application, for example, tailor-made ones, baguette flour or croissant flour or toast bread flour. Different applications are here available with different water absorption. With reference to the existing milling diagrams, there are different milling principles known. All of them take an influence on the starch activation. We are compare here a roller mill, a cylinder mill, with and indicated the forces of the particles with stress and shear. A ball mill, which we are using in our attrition process, even has a stress and a smooth of punch. Very known or even very old part in the milling diagram is a pin mill, which create an impact against the wheat flour. If we compare finally the influence on the water absorption and the effective water absorption, we can compare the roller mills with approximately 300 millimeters diameter compared to a 5 millimeter steel bead. The surfaces which are in contact with the material are very, very different. The cylinders are using just 0.5% of the surfaces to treat the material and increase the water absorption of, let's say, 3%. In the ball mills, the hexagonal structure of the balls provided a surface of 4.75%. This is the reason why the attrition grinding can increase the water absorption so strongly. And the next slide shows the results of these differences. An original flour is starting with, let's say, nearly 60%. Via a roller mill, we can increase up to 63%. The pinmill, we saw it before, has even an influence on the damaging of starch, but the energy what you invest is not in relation to the results what you're getting out. The attrition grinding is much effective, and compared to the water absorption what you can achieve between 80 and 90%, the energy invest is very low. Here compare pinmill and ball mill. We prepared here a spreadsheet where we are using a pinmill with 700 kilograms capacity in a single run, and we see we can increase the water absorption of 3%. Compared to the last column, the ball mill, even in a single run, we can increase even here 3%. But if we take now a look to the specific energy, we can compare 33 kilowatt hours per ton compared to 87%. None of these pinmills allowed us to increase the water absorption of more than 25%. Of course, the energy input is very high, but we are created here an additive, which is using in a erasure. On the search of analytic methods, we are and proper and verified analyzed methods, we have examined different relations. One of these is to realize or to analyze the activated starch. As we can see here, that is a sky of stars, which is not related to the energy input. This is a decision from us that the analysis of damaged starch is not possible for using in this process. Even we are a milling company, even we are analyze the particle sizes, which is typically a quality effect into. If you are compare here a pinmill and compare this one with a ball mill, we see that the particle sizes takes not the influence on the water absorption. When we are going back once, we have here a particle size nearly 50 microns and absorbed approximately 65% of water. And on the ball mill, we are much coarser, 84%, and absorb 66% of water. This follows to us that the particle size is not related to the energy input. Anyway, the water absorption is in focus, and this moved us to the Farinogram analysis for water absorption. The increasing of damaged starch absorbed a lot of water, and the Farinograph provides us the best result. This shown this diagram, the analysis of Farinograph on the vertical axis is related to the specific energy input. We can move the process on this line directly and adjust the request of water absorption. Very important on this flour is the rheological analysis method. Anyway, we would recommend it to coming back to the roots and starting with bakery tests, because the interpretation of analyzed results are very critical. If we are drop down the figures, 59 and 88% water absorption, everybody will bake this flour independent of yellow, of green or orange line. But of course, 88% water can be baked. This means that the recommendation from our side is, first of all, to starting with a baking test and then interpret the results. Even on the extensor graph, the similar situation is we have a typical curve, which is very difficult to interpret. The baking test are finally the solutions to find out the best one. beside of this, because we are machine manufacturers, beside of this we did some praxis results and invest some experience in bakery application. We are using here a French wheat flour with an unusual high protein level of 14% and runs this material through the attrition grinding process and increase this water absorption on 84%. In the first line, we shown a bakering result with 100% original flour. We have a bread yield of 120.6 grams per 100 gram of flour, and after 90 minutes you get this result of French baguettes. If you make now a blending of 90% original flour and 10% of our attrition flour, you increase the bread yield up to 124.5 grams per 100 gram of flour. This is the material what the bakers finally sold out. The next one is that the incisions and the colors are much better compared to the original one. We're getting browner and browner, and the incisions getting better. When we are using the 80% of standard flour and 20% of attrition flour, the bread yield is increased once more, and the colors getting more darker. Everybody knows fermentation time takes an influence on taste. This moved us to extend the fermentation time from 90 to 120 minutes. At 120 minutes, the original flour is not on the best shape, but if you are using attrition flour, the color and even the incisions getting higher and higher. Of course, even the bread yield is under the same direction as 90 minutes. Very common in Europe, maybe not in America, but even here we did some baking tests on wrap-up rolls. And what is very important, we have using a standard flour with 55.9 or nearly 56% of water and get as a result this material, this rolls. We get a bread yield of 126.3 grams per 100 gram of flour. If we are using right now 15% of attrition flour, we can increase the water absorption of nearly 60%. Very important, we increased, of course, even the bread yield. And this is finally the material what the bakers are sold out. So this 4% higher water absorption is directly moved into the bread yield. There is no evaporation in the oven time. And as longer the fermentation time, as worse is this one for a normal standard flour, and as better is this one for the mixture of attrition flour. We see it here. The incisions are more or less as the standard flour completely lost, and with the mixture of attrition flour and standard flour, we have no incisions, and we have the better quality available. Even here, we are transfer this 4% higher water absorption direct into the bread yield, into the wrap-up rolls. Cost situation, always very important, especially on the wheat flour, because the market is very hard in this matter. We did some examinations with a Switzerland milling unit, and in Switzerland they have the very nice situation that they already earn a lot of money for the wheat flour. I have here included a price of 25 Swiss francs for 25 kilogram wheat flour, which is very, very high. anyway, when they are using the standard flour, they have to have the cost of nearly 77 Swiss francs per 100 kilogram of bread. If you are at 10% of attrition flour and using 90% of the standard flour, we increase the bread yield of 1.5%. Cost-wise, we are nearly 2 euros cheaper, 1 euros cheaper as the standard flour. When we are using 20%, we have an increasing of 3 times higher bread yield, and the cost benefits getting higher and higher. This is finally the situation what allowed the millers to upset from the market. When we compare the material to the alternatives of increasing water binding additives, we have, for example, pre-channelized flour or guar flour. We have compared this in our feasibility study too. In Germany, 100 kilograms of wheat flour cost approximately 35 euros and can absorb roughly 60% water. In total, we get 160% of dough with a cost of 35 euros. 1 ton costs 218.75 euros per ton. Compared to the blending of 90% standard flour and 10% attrition flour, the doughing costs are reducing, not significant, but are on the same level, let's say. The cost benefit is available. Besides of this one, the qualities are much better, and the quality points are very important under this condition. If we compare a mixture of pre-channelized flour, 2.1 kilograms, and 97.9 kilograms attrition standard flour, the cost for this flour blending is roughly 36.05 euros. A ton of dough will be cost 220 euros, more than 220 euros, and it brings up a benefit of nearly 3 euros per ton. Guar flour, under this condition, we hope so the price are in the range which is acceptable. Is even one possibility, but has to be indicated on the label. The dough will be cost 290 euros compared to the original flour. We have a cost benefit of 1.4 euros per ton. And ladies and gentlemen, this is the last slide. The attrition grinding brings you up a possibility to work active on the market, independent of your national resources, and without any additional ingredients, just using the standard flour. Thank you very much.
Ladies and gentlemen, at this point, we'll take some questions and take a few minutes to answer those. And as again, we're going to put up the slide right now on the screen where you can see the contact information for me, where if you would like in the future, you can email us the questions when you have it. Alex, one question I see is, and I'm going to editorialize some of these questions since they're typed. I'm going to expand upon them a little bit. Is there an issue with containment from the steel balls in the attrition mill?
Yes. The steel beads will be there during the running time. This is the reason why we are using not a mixture of different ingredients. We are just using mild steel, pure iron will be the steel bead. Compare to the contamination of the iron, which is not toxic, but even not healthy, because we don't know under which conditions, chemical conditions, the steels are available. But compare, for example, to a normal wheat flour and whole wheat flour, for example, which has roughly 30 to 40 milligrams still available, the mixture of normal wheat flour and attrition wheat flour will be lower than a whole wheat flour.
Okay. I have one other question here, and it's, I guess, again, saying the attrition fraction has been shown as 10, 15, 20%. Can there be more added, and is the benefit, keep increasing?
Well, actually, we heard from our clients that they are increasing. Of course, I have to, at the beginning, I'm quite sure if somebody realized we can put 90% water into the dough, everybody will try it. But of course, finally, you won't be getting a bread out. The maximum what we heard is 20-25% additive. If you're coming up to 30% in ratio, the baking result will be getting like a gum. It's starting to be let's say gum. I think is the right one. Yeah, it's getting very sticky and the mouthfeel is not so good.
I see. And I guess I got one last question that I'm seeing right now is the question is there attrition flour available for testing? Is the question. My understanding is, I guess, could we provide attrition flour to the customer if they requested, so that they could do baking tests?
Well, finally, we have in our test center in Europe, we have the possibility to provide tests with the flour of the clients. If higher capacity is required, for example, if you would like introduce the flour into a frozen dough bakery shop, you need to have a bigger volume or a bigger amount. Then we can provide from a production line in Germany the flour, which you mix it up with your standard flour. This is a possibility. I think there will be find a solution to get the attrition flour to the clients.
Okay, that's all the questions I have right now. So I want to thank our audience for joining us, and I want to thank Alex for your time in presenting the material. And again, the contact information is up on the screen. If you think of any additional questions, please don't hesitate to either call us or send us an email, and we'll answer them as we get them. Thank you very much.
Thank you.